Hello everyone, this is continuation of our last lecture on kinematics. This is the second lecture on kinematics. To view the first lecture, you can go to the pinned link on your right and then you can see it. Okay, let's start. So in last lecture, we discussed kinematics, what is rest, what is motion, and how does these terms are relative to each other. And then we also discussed some of the scalar and vector quantity in terms of distance and displacement, speed, velocity, acceleration. And we also discuss what is average and instantaneous speed, right? Let's discuss what is average and instantaneous velocity, right? Average and instantaneous velocity. So what velocity means to us? Velocity is the ratio of displacement to time, right? So displacement per unit time is nothing but velocity, right? But these terms, average and instantaneous velocity, let's discuss what are these. So let's say this is a nature of displacement time graph. Let's say I'm representing displacement by s and time by t, and let's say this is how displacement time graph looks for any object or a particle, right? And if I'm given two instances, right, t1 and t2, t1 and t2, right? So between T1 and T2, if I need to calculate is this average velocity, average quantities depend on the interval only, right? They are not bothered about what is happening in between, right? So if I need to calculate average velocity between T1 and T2, what I basically need is I need the displacement at this point, let's say S1, displacement at this point, let's say S2. Let me call this as vector form, maybe for now, yeah, because displacement is a vector quantity. And if I need to calculate this average velocity, it will be what? It will be nothing but change in this position vector. This may be a position vector also if it is represented vertically with respect to change in time, right? Change in position vector with respect to change in time. If in vectorically, if I want to represent this, I can also represent like this. Let's say this is position vectors. I'm plotting it on xy plane, right? And this is, let's say, r1 vector, right? R1 vector, and particle is at point t1, it is at r1 vector, right? At point t2, let's say if it moves to r2 vector, right, then what will be my average velocity? It will be nothing but r2 vector minus r1 vector by t2 minus t1, right? So this is how we calculate average quantities, right? Now let's talk about what is instantaneous velocity. Instantaneous velocity. So again, to calculate instantaneous velocity, the tool which we have is differentiation, right? Instantaneous velocity gives velocity as at a specific point. So we need to, let's say if I am calculating at this particular point, so we need to draw a tangent at this particular point and find the slope of that tangent, because the slope of that tangent give me the minimal change in displacement with respect to minimal change in time, which is basically instantaneous velocity, which is at this particular instance. Let's say this is time t and the name is p, right? So if I need to calculate instantaneous velocity, let me call this as v inst. This will be nothing but differential of this displacement with respect to time at time t, or let's say point p, whatever value of the coordinate is at point p, right? This is how we can calculate the instantaneous velocity, right? Now let's talk about average and instantaneous acceleration. Average and instantaneous acceleration, again, it's all same. Average and instantaneous acceleration, right? So how we discuss velocity, the same will go for acceleration also, but when we talk about acceleration, we talk about change in velocity, right? So let's say we have a velocity time graph, right? Velocity time graph, something like this again, correct? Again, at, let's say, at t equal to t1 and t equal to t2, if I need to find this average acceleration in this duration, it will be nothing but, let's say this is v1 and this is v2. So average acceleration, let's say it will be v2 minus v1 by t2 minus t1. Clear? What about instantaneous? Instantaneous acceleration at any point will be given by rate of change of velocity with respect to time at a given point. Let's say at point p in curve, right? So this p will have some coordinate, v and t coordinate. So at this particular point, if I differentiate velocity with respect to time and place this value, what I will get is instantaneous acceleration at that point, right? Okay. So we understood what are average and instantaneous quantities and how differentiation as a tool can help us to find instantaneous values of differently varying graphs, right? Okay. Now let's discuss a very important topic, which is motion in a straight line. Motion in a straight line, right? You might have studied these type of motion from your junior standards as well. You know what is rectilinear motion and things like that. So motion in a straight line, it basically tells me that object is moving along one particular straight line, right? And to represent motion of that object, I just need one coordinate. Let me just explain. So we know this xy curve, right? Xy curve. This looks like this. So motion in a straight line means my object is moving along one direction. It has nothing to do with this particular direction, right? So it is moving either along x or either along y, but no, it does not fall in this particular region. Which, because if it falls in this particular region, then I will need both the coordinates to represent that motion, and then it will become motion in a plane, right? This becomes a plane. Motion in a straight line means I just need one axis. Let me remove this one completely. I just need x-axis to represent motion of a particle, right? So if this is x-axis, I can say, let's say this x is my displacement. So I can represent all quantities in this particular motion, right? Let's say x is displacement. I can say x is nothing but displacement, right? Again, what I will say, dx by dt is velocity, instantaneous velocity, right? Which is v, right? What is dv by dt? Dv by dt is acceleration, right? Now if dx by dt comes positive, right? If dx by dt comes positive, this basically means the object is traveling along the positive x-axis, right? Because change is positive. If dx means positive velocity, if dx by dt is negative, which means negative velocity, it means object is traveling to the left of x-axis, right? In this direction. Similar for dv by dt. If dv by dt is positive, which it means object is traveling towards the right with positive acceleration. If dv by dt is negative, it means object is traveling towards the left, right, with negative acceleration. Correct. Okay. Now, in motion in straight line, let's discuss one more scenario. The scenario says motion with uniform acceleration. Motion with uniform acceleration. Now we already know the acceleration can be of two types, right? First type of acceleration is uniform acceleration, which basically means the velocity changes by equal interval of time, right? Which basically means the parameter a of acceleration is constant throughout the motion. And then there is a case of non-uniform acceleration, where velocity can change randomly and it does not follow this pattern, right? So now we will discuss this specific case, which is motion with uniform acceleration. And you might have come across these terms, which are equations of motion. How do you derive v equal to u plus at, s equal to ut plus half at square, and things like that. And you will understand that those equations are only valid when your acceleration is uniform. The time when acceleration becomes non-uniform, those equations will be just equations. They won't be valid for that particular situation, right? Okay, let's derive those equations using this particular topic, right? Okay, you know, acceleration is nothing but it is given by what? Dv by dt, right? V is velocity, v is velocity, a is my acceleration, and t is obviously time. So you know, acceleration is dv by dt, right? Change of velocity with respect to time. If I calculate dv, it will be what? A dt, the just simple cross multiplication, right? Now if I need to calculate velocity from here, right, what I need to do? I need to integrate here, because integration of dv will give me v. How? So integration of dv means integration of 1 dv. It basically means integration of v to the power 0 dv. You know formula of integration, it becomes v to the power 0 plus 1 by 0 plus 1, which basically becomes v. So integration of dv will give me v, which is velocity at that instant, right? But let me put the limits, right? Let me put the limits. Let's say I'm integrating the quantities and I'm considering at time equal to 0, my velocity is u. At time equal to 0, the velocity is u. So u becomes my what? Initial velocity. Initial velocity. And at time equal to t, my velocity is v. At time equal to t, my velocity is v. So v becomes, now this cancel this one, v becomes my final velocity, right? So now integration of v is v, the limit is u to v, and acceleration is a constant here. We are talking about a case of uniform acceleration. Acceleration will come out of integration since it is a constant. We can safely bring it out. Differentiation of dt will be again t from 0 to t. Now let's put the limit values. So the upper limit is v, lower limit is u. We'll subtract. This is how we do definite integration. And then this is a t minus 0. So v minus u equal to at, and this becomes v equal to u plus at, right? So this is how we derive the first equation of motion using calculus method. This is how we derive first equation of motion using calculus method. Just assume that a is here is a constant term because we are dealing with a case of uniform acceleration, right? Right. Now let's derive another equation of motion using same calculus method. Okay. So we derived just now, we derived what? We derived that v equal to u plus at. This is what we have in hand, right? Now for second equation of motion, we know that velocity is given by rate of change of displacement by time, dx by dt. Velocity is nothing but dx by dt, right? Now if I again do a cross multiplication, dx will become what? V dt. Dx will become v dt. Now if I need this v, can I get this v from this equation? This final velocity, can I get from here? Right. If I place this v here in this term, what this becomes? Dx is equal to u plus at into dt. Right? U plus at into dt. Now dx becomes u dt plus at dt. Right? U is what? U is my initial velocity. X is my displacement, t is my time, a is my acceleration, which is a uniform acceleration, right? Now I am going to integrate this particular quantities, right? Let's integrate. So at time equal to 0, these two are with respect to dt, so time equal to 0. Let's say my displacement was x naught. X naught was my initial point where I'm starting from. At time equal to t, let's say this displacement was x, right? Now integration of dx is x. Limit is from x naught to x. X naught is what? Displacement at time equal to 0, right? X means displacement at time equal to t seconds, right? U is my initial velocity, it will come out as constant. This t, a is my acceleration, again constant, it will come out. T dt integration is t square by 2. T square by 2 from 0 to t. Now let's put up the values. So this becomes x minus x naught equal to ut plus at square by 2. X minus x naught equal to ut plus at square by 2. Now if I find x from here, x becomes x naught plus ut plus at square by 2. This is my final second equation of motion, which basically said x equal to x naught plus ut plus half at square. Now you would have studied x equal to ut plus half at square. There is an extra term x naught here. So when we derive s equal to ut plus half at square, we assume that at time equal to 0, the particle was at 0th coordinate, right? It has not shifted from its position. So we are starting from origin. But if in question it is given that at time equal to 0, particle starts from 3 meter, 4 meter or 5 meter, we need to put that initial value here and then we need to apply this particular expression, right? So we for a special case, I can say that if x naught is 0, my x equal to ut plus half at squared. But this is not enough to know. You need to know that if particle is not at 0th position at time equal to 0 second, we can't directly use this particular expression, right? Now let's derive the third one. So we have derived two equations of motion till now, right? One is v equal to u plus at, and another conditionally I said that it is ut plus half at square. This is a conditional. Okay, now let's derive the third one. So for this third one, acceleration is nothing but dv by dt. Acceleration is nothing but dv by dt. Can I break this via chain rule, and can I write it like this? This is dv by dx into dx by dt, right? Dv by dx into dx by dt. This particular term dx by dt is what? This becomes velocity. So can I write it again like this? V dv by dx. So acceleration becomes v dv by dx, right? Now if I need to calculate velocity, can I put it like this? V dv equal to a dx, right? Let's integrate. Let's integrate here also. Let's say that when my initial velocity is u, right, at time equal to 0, my initial velocity is u, and my position is x naught again. At time equal to t, my final velocity is v, my position is x, right? So this integration will become v square by 2 from u to v, and this becomes ax from x naught to x. So this becomes v square minus u square by 2 equal to a into x minus x naught. So this basically becomes v square equal to u square plus 2a x minus x naught. Again notice here that I have taken a quantity called x naught, which basically indicates position at time equal to 0. So if this position is 0, if my particle is at origin at time equal to 0, I can simply say v square equal to u square plus 2ax, which you all know, which is the third equation of motion. Let's write all three together now. First equation of motion, which is v equal to u plus at, right? Second equation of motion, x equal to x naught plus ut plus half at square. And third equation of motion is v square equal to u square plus 2a x minus x naught, right? Now let's put the meanings of these variables. V is my final velocity, u is my initial velocity, a is my acceleration, which is uniform, t is obviously time, x is position at time equal to t seconds, x naught equal to position at time equal to 0 seconds. And using this particular equations of motion, we can actually solve a lot of problems of motion in a straight line where we have constant acceleration type of condition. For example, in case of free fall, right? Free fall. If I'm letting a body fall from some height and I'm ignoring air resistance and all effects, hindrance and things coming up, it is under effect of gravity. So it is going down with acceleration which is supplied by gravity, which is called acceleration due to gravity. So in that particular case, we can use these three equations and find the position of particle at an instant, velocity of particle at an instant, acceleration we obviously know. So those type of problems we can find. So let's derive this equation for free fall also. Right, so we discuss equations of motion, and we also discussed that those equations, as how we derived it, they are only applicable where we have condition of uniform acceleration, right? So they are not relevant in a condition of non-uniform acceleration. And the best example of uniform acceleration is acceleration due to gravity, right? So free fall, what basically means this term free fall means is an object is allowed to fall freely, or an object is under influence of gravity and we ignore all other effects like effect of atmosphere, air, anything, and it is only under the effect of Earth's gravitation. It might be thrown upward from Earth, it might be thrown downwards to the Earth, but it is only under the effect of gravity, right? So there are two cases, upwards and downwards. If object is thrown from Earth to some height, Earth will act as a opposition force for it, right? The Earth's gravity will be a opposition force for it, and hence it won't basically support its acceleration, and there will be a case of retardation, right? There will be a case of retardation, and here if you see acceleration will be nothing but it will become minus of g meter per second square, right? In case of upwards. But if I throw a ball downwards from some height with only effect of Earth, the Earth will support its acceleration, and acceleration will be what? It becomes plus g meter per second square, right? Now I can apply all those equation of motion, and I can put these values, right? Can I put the values and say that this becomes v equal to u minus gt, first equation? This becomes x equal to ut minus gt square by 2, second equation. Third becomes v square equal to u square plus, sorry, not plus, this becomes minus 2gx, equation 3, assuming that x not equal to 0. Initial, I am considering 0 as of now. Again, this becomes v equal to u plus gt, equation 1, x equal to ut plus gt square by 2, equation 2, and v square equal to u square plus 2g x, equation 3, right? So yeah, this is how we can use these particular relations depending on question whether it is a upward free fall, downward free fall, and we can solve different numerical problems using these equations, right? So let's solve a problem using the equations of motion. So the problem states a particle starts with an initial velocity of 2.5 meter per second. Let's note what are given quantities. U, which is initial velocity, is 2.5 meter per second along positive y-axis, which basically this is a problem of motion in a straight line. It accelerates at this particular value 0.05. So acceleration is also given plus 0.05 meter per second square. So acceleration is uniform. We can safely apply equation of motion. First, we need to find what is distance travel in first 2 seconds. So time is nothing but 2 seconds, right? For first problem, for let's say for A part, time is given as 2 seconds, and we need to find what is distance. Since x naught is not given, we'll assume x naught as 0, right? For second part, what is given is how much time it takes for it to reach to velocity of 7.5 meter per second. So we are given final velocity which is 7.5 meter per second. We need to find how much time it will take to reach to this particular velocity, right? Let's start with first problem. Let's start with the A part. So for A part, what we know? We know u, initial velocity. We know A also. We know t also, and we need to find x. So we need to think on what equation we can put up and what equation we can use to solve this particular problem, right? So equation which comes to my mind is x equal to ut plus half a t square. You see, you have all the values. You have u, you have t, you have a. You can easily find x, right? So u is nothing but 2.5. Time given is 2. Acceleration is 0.05, and this becomes 4. This becomes 5. 2 into 0.05. This becomes 5 plus 0.1. This becomes 5.1 meter, right? This becomes 5.1 meter. I hope my calculation is correct here, right? Okay, let's solve another part of this particular problem. Another part says we need to find time it takes to reach a velocity of 7.5 meter per second, right? 7.5 meter per second. So to solve B part, again I know what? I know this final velocity is 7.5, initial velocity is 2.5, acceleration is 0.05. I need to find what is t. It's very simple. I'll go and use this particular expression, and I know this t is nothing but v minus u by a, which is 7.5 minus 2.5 by 0.05, which is nothing but 5 by 0.05. If I'm not wrong, this becomes 100 seconds. Right. So in 100 seconds, this particle will reach from 2.5 meter per second to 7.5 meter per second if it maintains this particular acceleration. Right. Right. Let's discuss this new topic, displacement in nth second. Right. So we just derived an expression to calculate displacement, which was x equal to ut plus half at square. How this topic is different from that particular expression, right? Now, in that particular expression, if I use this x equal to ut plus half at square, if I am given acceleration, initial velocity and time, I can derive what is distance travel. But I can say what is distance traveled in t seconds, right? But I can't say what is distance travel at the tth second. Okay, let me give an example. If an object travel from 0 to 10 second, right, I can easily calculate how much distance it travel from 0 to 10 second, which basically means in this duration. But what if I need to calculate how much distance it traveled in the 10th second, which basically means when it was going from 9th to 10th second, how much distance it traveled in that particular amount of time. This won't be clear by this equation. We need to have an equation for this as well, right? Are you following this? So if I need to calculate how much distance this particular has traveled in the 10th second, which is the last second, this equation will not help me with that. This will help me, but I need to modify this a bit to get through, right? Now let's take it like that. If I need to calculate the distance travel in the 10th second, which basically means when between the interval 9 to 10, how much distance it travel, can I calculate distance traveled by this in 10 seconds? Can I calculate distance traveled by it in 9 seconds? And if I subtract these two, I'll be getting the displacement of 10th second, which is the nth here, right? If I, if let me repeat, if I calculate distance travel in 10 seconds and subtract that by distance travel in 9 seconds, I'll get the distance traveled in 10th second, right? So using similar strategy, if I need to calculate distance traveled in nth second, I'll calculate this distance traveled in nth second. I'll calculate distance traveled in n minus 1th second, and I'll subtract these two distances, and this will give me the distance travel in nth second. So if Sn is my distance travel in n seconds, so if this is distance traveled in n seconds, and s minus n minus 1 is the distance in n minus 1 seconds. So if I subtract Sn minus 1, this quantity will give me distance traveled in nth second, right? Okay. Now this is very simple. We can derive this. So distance traveled in n seconds will be given by what? Xt. So I'll use xn here plus an square by 2. This is my equation 1. Distance traveled in n minus 1 seconds is xn minus 1 plus an minus 1 square by 2. This is my equation 2, right? Now to calculate what is our problem statement, distance, this can be displacement as well. So displacement in nth second, if this is Sn and this is Sn minus 1, is nothing but Sn minus 1, which basically is 1 minus 2. So if I indicate this by xn maybe, so this becomes what? This becomes xn plus an square by 2 minus xn minus 1 plus a n minus 1 square by 2. Clear? Right? Right. Okay, yeah, this is not x, this is u everywhere, s equal to ut plus half at square and not x. So this becomes u u u u. Can we solve this now? Let's solve this one. So this becomes u if I take this and this together, and if I take these two together, this becomes a by 2. It is nothing but n square minus n square minus 1 plus 2n. So this becomes u plus a by 2 into 2n minus 1. This is nothing but displacement in nth second in meters. U is my initial velocity, a is my acceleration, and n is that instance of time where I want to calculate this particular displacement. So this is the general expression to calculate displacement in nth second, and this is very useful where you are set to find displacement at a particular fraction of time and not in the whole duration of journey, right? Okay. Right, so we discussed motion in a straight line, and we derived equations of motion for the case of uniform acceleration, right? For the case of uniform acceleration. And extending to that, we also derived how can we calculate displacement in nth second using this particular expression. In next lecture onwards, we will be solving problems on these topics and formulas, and then we'll be starting motion in a plane where we'll be discussing the motion in a 2D geometry, right? Till then, thanks.